Where's Alan?
Alan's helping James.
Okay. I guess I'll wait for that. Or I'll just go.
Construction.
Sit down. It's so hot today.
That's a guide at some point. Okay.
Oh yeah, so basically,
So then
one side of the drive face works,
we're gonna
and
draw
I
4
put
circles
in one
the corner.
gearbox.
Yeah, draw
Nice.
So
circles.
then I'll
circles.
connect them next meeting, and then hopefully it'll be done.
Is the Neo still not quite
Oh, you hit the circle.
still holding on?
Oh, okay.
And then
Did we go with the
so
wire?
like the center point, which is
I
the
mean,
corner
the
of
wire's still on, it's just that,
rectangle.
There's no connector.
yeah,
And draw the circle.
Okay.
and there's no way
Or
to
you
like
just click it
replace it right now.
Yeah. It'd be good to let
So the fun
James
part
know, I guess.
is
Although he probably
then you
already
want to
knows.
use the equal tool, the equal signs. You make the circles the same size.
Alright, I guess I'll just start. So, feel free to ask questions. You know, I don't really have as much of a presentation today. We're just going to look at this,
Okay.
and then we're going to go
So, yeah,
through
drag
a bunch of
this. I select
situations
the
for
corner.
when you would, like
So
how to
now
make a
the next
reduction
step
for a
is
certain
probably to set
subsystem.
the sizes.
So,
So
do you remember what the yellow line is?
oh, sorry.
The
yellow
So
line is stall
you
torque.
hit to do
Huh?
the equal thing.
Yep.
So,
Okay,
so
sounds
you
good.
hit equal,
Um,
and then you hit the first
the-
circle. and the
okay,
second
so
circle. That makes sense.
so the yellow line is stall torque. The bottom, the x-axis is RPM.
Now, because I'm editing,
The blue line, the blue dash line,
this.
that's current. So as you can see, when you're at stall torque, you're at max current. And then when you're at free speed, you're at the minimum current, which is usually around like a few amps. And stall current is usually around 100 and something amps, right? You know the breakers are like 40 amp breakers, right?
I guess this whole thing is basically just
Or 30 amp breakers.
Is basically just
James
assigning
knows that. So why doesn't the breaker just pop every time we go above 50% stall?
So for
Because
instance-
50% stall is like 50 amps.
If I select the 2 circles here,
Because it doesn't cut it immediately.
Yeah.
It waits for a
then you
bit.
can see
Yeah.
that-
So the 40
right,
amps
it tells
is
you
basically,
the- it
generally
tells you the
speaking,
X and
it's
Y.
just
So
the,
basically I'm using
uh,
the rectangle to be these
it's the,
sizes.
if you're not above
Specifically, the circle
40 amps,
stops
it's guaranteed
outside
not to
of
pop.
the box. But yes,
basically.
I can basically
Um,
do this.
So it, and the higher your current draw above 40 amps, the faster it's going to pop.
Here.
So if you're at 130 for like a second, it's going to pop.
It's not
Yeah.
necessary.
And then when it pops, does it permanently break the breaker?
No. There's a difference between a fuse and a breaker.
Oh, okay.
A
Yeah.
breaker can
Just
pop
disconnects
back.
it?
So it's, I think it's like a second
So
So, before it pops back. So sometimes you'll hear this like popping sound with the breakers.
Mhm.
That's the breaker popping back and forth. The main breaker will pop, but it doesn't automatically pop back. A
Yeah.
human has to come in and
Right.
pop back. So if you
It's
you
a
go
physical
above
pop.
120 amps for too long and you pop your main breaker, which 254 has done on multiple occasions. In 2014 they had problems. Then
Aerial assist, really?
yeah, their world championship robot. Yeah.
Circle.
Then
Circle.
it might be in trouble. I think but part of it was such a pushing game, right? So I think that had an impact. The red dash line, that's efficiency. So when are you going to have the highest efficiency?
Around 18,000 RPM.
At 12 volts.
Yeah, this whole chart is assuming a 12 volts,
Oh, okay.
right? Do you remember how the stall torque varies if we were like at 6 volts?
Yeah. It'd
be half
just
that.
linearly.
Yeah, so it'd be, instead of this line, it would be half of that. Because it would be halved at every point. Sorry, what did you say before that about 12 volts? You said this chart is for 12 volts, or what were you saying?
Oh, I was saying max efficiency, but 18,000 RPM is max efficiency.
Yeah. So usually max efficiency is like 8 to 12%, something like that, or 18 to 15%. It's like max efficiency. 8 to 15% stall torque. So usually really low torque is mostly much more efficient. Why do you think that at full free speed that's not very efficient?
You want to snap the circle of the sketch to the circle
Because the extra amps that it has to
of this. Equal to equal
use to
size.
spin it are
I'm going to delete this too.
harder to give.
Go equal
Uh-huh.
size of this whole size. Of
What
this
what
I don't
did
know
you
if
say?
You guys got it. He said, what did you say again?
There's basic.
So it's
No
like two
torque.
circles.
Yeah, that's the
Basically,
closest.
shared same
When there's no torque, you're not doing any work. So you're
That's
zero.
what
So you're not
efficient.
moving. Yeah.
trying to show you what's happening here. So it's two circles
Oh.
in the same center.
Yeah, you guys have
So it-
physics.
yeah.
So like these two
But,
things.
You need some small amount of torque.
Yeah.
So
Otherwise,
it's
you aren't
doing
moving.
something. Okay.
I guess we'll talk about work for just a second. So, work is where you push on something over a distance, right? Torque is the push for rotation. So if you have torque over some rotations, you've done work. But at free speed, you're not. You have no torque.
The last
So
You
it's just
can't
spinning.
possibly do any work, right? You're
you
doing no
really
force.
only have to do two
So
before
you've
corners.
done zero work,
Because
and you've
otherwise-
expended some current. There's like a 2 amps or whatever it is there at some number of volts, 12 volts. So yeah.
Wow. Okay, so it's a little manual. You have to draw this.
Yep. So that's efficiency. What's the green curve?
Not attached to that.
Out.
Power, output power
Yeah.
in watts.
So
So
we
this
talked
is where
about
the
work,
thing comes
which
from.
was
If I want these
like
two
how much
to be
energy
exactly in the same
you're
place, all three,
putting
that's
into
why
doing
you
something.
can hit this.
That makes
and then-
sense, kind of.
Oh.
Power is just how much work you're
Considering
doing
this
every
is three
second.
dimensions,
So if you're pushing something really heavy, really fast, you're doing a lot of.
Concentric.
That's very powerful. But if you're pushing something really heavy very slowly, you're doing
along the same line.
not as much. You're not exerting as much power.
That's probably it.
So
These things will-
because in
makes
FRC
sense.
everything's timed and you want to do things really fast, generally you want to be more powerful, right? If your climb's more powerful, you can lift your robot faster in a shorter amount of time.
Okay.
So generally, you might want to design all your motors to operate at max power
Go.
because then you could do things really fast, right? Any idea why we don't design for max
Okay, so
power?
In case your battery is lower than 12 volts.
It
Wears
will
down.
remove.
Your battery's lower than 12 volts.
And you hit the circles.
Max power would
Yeah,
still
this is how you
be.
get.
Yeah,
Brownouts?
torque would be less.
Like
Brownouts, yeah, that's interesting. That's interesting. Yeah, you guys are kind of right.
I'm still learning this. So, yeah, so
Because
remove,
it's
remove,
engineers are conservative, and notice when you're at your efficiency is better down
this circle.
when you're at lower percent stall torque, but it's kind of more complicated. I guess I don't completely understand it, but the general idea is
So basically, you want to select all
you
of
design
the inside
for
circles.
like 20% stall torque over here, and then if let's say your arm runs into something, now you have more power that you can give.
And then we'll drill a hole.
So you move up, right? When the load increases, you're going to move up to a larger stall torque.
Mm-hmm.
So you have kind of more you can give, and also you're when you're inefficient, the motor heats up, and then it's even less efficient because hot wires are less conductive.
So if I hit green check mark,
So
now we have a board of holes in it.
you basically do not want to get at the point where you're just like kind of running it away with. Yeah, you don't want to get past the halfway point. That's very bad.
How do you limit the, if you're
If we
outputting 12 volts to a motor, how do you make it run at only a certain stall torque?
and then we click away.
The free speed and the stall torque are linked.
So how do you limit the free speed if you're giving it 12 volts?
Yes, that's a good
Because it's
question.
in the holes.
I would basically say you have a load on the arm, and that's the amount of torque you need to exert. So that's limiting what the torque is. So these motor curves are given a certain situation. So you can think of it either way, honestly. You can think of it given it's going a certain RPM, how much torque does it have? Or given a certain torque, how much RPM is it going to be going at? It's kind of like, you guys haven't done Ohm's law, but it's kind of like Ohm's law. Everything's all related. This relationship just, it's dependent. It's very related to Ohm's law here.
So when you put a load on it, it will limit how fast it can spin.
Yep. Okay, you guys haven't taken physics, so this makes this a lot harder. You need more torque to accelerate. So if you're at zero speed, then it's, even though the load is lower, you're going to have a hard. Okay, great. So
I would put the dimensions in manually. But edit in context is still useful because
Yeah.
you can see it in real time.
Yeah, they're just interrelated. So honestly, it's just so much simpler to think about it at constant speed. Just to think the motor's going at constant speed, you've already made it up to speed. So that's honestly how we do it because it's a lot easier. It's pretty close, and the way that we tend to do things is we just pick a gear reduction that's close, and then we try a whole bunch of things that we're like, oh, we need it to be slightly faster. Let's see if changing the gear ratio helps. And if it doesn't, then we might add another motor. So we're very, because this is kind of complicated, we don't really hone in on all of the details. We just come close.
So this one already had dimensions.
Yeah, I guess that's all I'll do for this.
Then the last step is
so like I just said, we get close. We design for 20% stall torque. So if you're designing a motor, just start with 20%, whatever loaded situation you have. Like I said before, when things are complicated, when there's multiple factors you don't understand, generally a good solution is just to prototype. So you start with something, and then you make an educated guess about what's going to improve the situation, and then you try that, and if that doesn't work, great. So this is a general thing that works pretty well in complicated situations.
So basically, one side of the drag disc works, and I put in one gearbox. Okay.
Oh, and James, one of the Neos doesn't have wires.
It's not crimped?
No, it got ripped off or something. I don't know.
Wait, what?
The connector isn't there.
Yeah,
Yeah.
it has wires,
Yeah.
right?
Yeah.
It has wires. There are wires coming out of it.
Yeah, the wires come out.
Okay, good. And
Yeah.
I thought you said that the wires were gone.
Yeah, that's what I heard too.
There's also like, there's like a limp spot in the middle of the connector wire.
Oh.
Yeah.
Oh, the encoder.
Yeah.
I know what you're talking about.
Yeah.
That's fine.
Great.
Okay.
Yep. One thing to note is motors die when they're stalled. So if you go to the high, if you
I would worry about for this right
if you
now.
lock up the
I think we're
rotor
gonna
or you
make
have
this
too much of a
high.
load on the motor, it's going to stall. And
We'll
if you
figure
stall
out
it for
a way
too
to
long,
raise
it
real
will
size.
break, just
And
like
we'll
a fuse.
Do it manually by hand.
Yeah. So that's actually part of the reason why you want to design
So
at
the
around
part that I think is
20% stall torque,
is
for
figuring out how to
the
fit this.
because that does it can generally sustain that for a very long
Honestly, I
period
would
of
put it
time
right here.
without dying.
I would probably just scooch these over and put this here.
Other teams design for like 18 to 30% stall torque, but and we traditionally have designed for like 30% stall torque. But I think I'm kind of thinking for this upcoming season because the robot's going to take more abuse because we're going to be doing drive practice more, and we're definitely going to champs, and
We have the thing.
it might just
Does it have wires?
design at 20%. Yeah. So sometimes it's tricky to figure out how many motors you should use. Generally, you just up the motors if 20% stall torque is not working out for how fast you want the mechanism to be. It's pretty simple. So we'll go over each subsystem and what general goals I would have for the subsystem. Sometimes you might also want to change the number of motors because you can't get a reduction really easily. You're like, well, if we add a motor, we can just throw it in an off-the-shelf gearbox and it gives us the right stall torque. Right? Because if you have more motors, you have a higher torque and you need less of a reduction. Does that make sense? Also, having extra motors can be nice because it can be redundant. So like maybe you have a situation where if one of your motors dies, you're still okay.
It's this thing.
Or you can try to make your mechanism more powerful
This
so
is
it
the PDB.
does the thing faster, or you can make it more efficient,
See how-
right? Because we saw the efficiency curve. If we have a lower percent stall torque, then our motor is more
see
efficient.
how the-
And you might want that for some
these
reason.
two holes of those
Um,
holes. So See how you
Okay,
can't really
so
put
for
it-
arms, generally you want to gear them as slow as possible.
But you can put this.
Because if you turn a motor on and the arm just goes, right, that's not very useful. You don't really have much control over it, and it makes it a lot harder for programming. So
you can put this here.
if you don't have really good programming control loops, it's good to have the arm motor go slowly.
Put this.
So generally, an arm motor going slowly isn't a bottleneck. So why not have it slow? So if you notice this year's robot, we geared it at like 300 and something to 1 for the arm. But we technically did not need it to be geared that far down, I think. Or actually maybe we did. I can't remember. But generally, you want arms to be slower because it just makes programming job easier. It makes it so much easier. Just make it slow. You have so much power these days. It doesn't really matter. You want to add more motors to an arm when it's way too slow. Sometimes arms are like, it takes like 4 seconds to get up to the correct point. It's probably too slow. And if you can't get enough torque with a single motor, you might want to add a second motor. That's generally the lesson. Do you guys know about types of motors that you use, like Sims?
Neos are stronger than Sims.
Yeah, that's true. That's true. So generally, there's closed motors and there's open motors. Sims and mini Sims and bag motors are closed motors. They're generally heavier. They basically have a heatsink built in. So they have a lot of metal to hold a lot of heat, right? And they're generally much more robust. The open motors have a fan, like a plastic blade, that when it spins, it moves air around, and it cools the motor. So you'll see on the Versaplanetaries and stuff, there's actually like a little gap between 775 Pros and the front of the motor because it wants to leave space for air to be able to go in the front of the motor so that the fan can draw air through the motor. Right? So it's very important that for open motors, you allow air to come in where it needs to come in and leave where it needs to leave because it needs to cool itself. Generally, open motors don't like to be stalled for very long. They'll die very quickly if you stall them. Whereas like a Sim will die much slower. So that's traditionally why Sims have been used on dry bases and stuff like that because they're much more robust and you can stall them so you can like get in a pushing match and like where both robots aren't moving and you're still okay. Some teams have actually used 775 Pros and they've had like an active cooling system where they force feed air through the 775s to keep them cool, even when they're stalled. Neos are brushless motors, so I'm not going to explain the details of a brushless motor, but I don't really understand brushless motors that well. But the Neo's behavior is more powerful than a Sim, and it's like somewhere between a 775 Pro and a Sim for how robust it is. So you really don't want to stall it for that long, but it's pretty good actually. So Neos are awesome actually. Open motors tend to be lighter than closed motors. I guess I already said that. Yeah, great. So for arms, generally, you'd see people using Sims and mini Sims a lot because arms tend to be stalled. But if you design correctly, so like if you design for 20% stall torque at the worst case, then stalling is not the worst thing in the world. In fact, that's another reason why you might want to have a slower arm because now you're only at like 5% stall torque, and now stalling your 775 Pro is not that big of a deal. Okay, so the goal for elevators is about the same. You want to get to your position in about a second. And I'd use a 775 Pro or a Neo. Some people have in the past used Sims or have used powered takeoff. Do you know what powered takeoff is?
Does it have anything to do with pneumatics?
Yeah, it's something to do with pneumatics. It has to do with you have your drive gearboxes, right? But when you're climbing or doing something in particular, you might not be using the drive base. So what people did was they would have a pneumatic that would cause the drive base gearboxes to shift. So they're no longer connected to the wheels of the drive base, but the gearbox is connected to like an elevator or like a climber of some sort. So it's a way to change what your motors are connected to by throwing a pneumatic. That's not super relevant to this, mostly for climbers, but and I think in this day and age, power takeoff, generally you don't want to use power takeoff unless you're like really short on motors. Again, elevators aren't usually the bottleneck. Generally, you see like 2 motors on an elevator, that's pretty normal. And if you're using it to also climb, you generally see 3 to 4, maybe even 5 motors on an elevator. Intakes, the goal is to get the surface speed of the wheel to be 1 or 2 times the max drive base speed. So let's say you have a 2-inch wheel, the circumference is 2 pi, right? If that's going 1 RPM, then it's going 2 pi inches per minute, right? And your goal is to get that intake wheel going as fast as your drive base, or a little bit faster usually. I don't know, did you see this year's robot where Hubert could like go full speed into a ball and pick it up? Yeah, or like that would not be possible if, or go full speed away from a ball. That wouldn't be possible if the intake speed weren't fast enough. Right, because when you're going towards a ball, if your intake is spinning slower, then it's actually going to be, you're just shoving the ball in without really taking it, and it could bounce away or whatever, right? So generally that's the goal. For intakes, torque requirements are hard to calculate because usually most of the resistance is from squishing a ball or squishing whatever you're intaking. Or squishing your compliant wheels, whatever you're squishing. So the torque requirements are kind of hard to know. So generally, for intakes, I would shoot for the 1 to 2 times the max drive base speed, and then if you don't have enough torque, you can add a motor. 775 Pros are good candidates for intake motors. Neos are now a good candidate. And bags are sometimes a good candidate if you're expecting to stall your intake a lot.
That actually works.
Because if you, yep.
I think there's this much room right here. So if you move this over so that the post is in this open space, then you can attach
climbers.
this.
You want climbers to go as fast as possible. If you have more motors, you can just throw more motors at your climber. And you generally want climbers to be as fast as possible.
Move towards the real.
So you just basically do a motor calculation. You're like, okay, 20% stall torque, and then you just you don't do the calculation off the speed. You mainly do it off of just maximizing power, right? Because if you're around, if you're at 50% stall torque, you're at max power, but that's going to kill your motors fast and it's not the best. So maybe even 30% stall torque for a climber might be a reasonable thing to do if, because climbers aren't used that much. So, damage on a climber mechanism is not that big of a deal through FRC seasons. FRC seasons are getting longer, but it used to be you'd only play like 12 matches in an entire season, and then like, who cares if you're burning your motors out a little bit? So I would just design for 20% stall torque for climbers and just say that's good. There's another way to design motor systems where you go through the whole cycle of where the motor starts at stopped, right? And you figure out how much energy you have to put in at each time increment. You do an integral or something, but you guys don't know what that is. Yeah, there are different ways to do this. In 2017, for a dry base, we did an additive model for figuring out the dry base speed, and that worked relatively well. But because we use versaplanetary so much,
Okay, so see how it's saying this drawing should be
just-
updated?
just get close with the
Your
calculation
drawing one.
and then try other stuff. Like generally, that's our philosophy. If you're making a custom gearbox, you have to be more vigilant. But if you're just doing what we do, which I think is a good policy, is just throw something on there with the versaplanetary and change it if you need to. Just do the calculation, get close, and then figure it out
See
from there.
The circle arrow? Yeah, update the workspace.
Do you have any questions?
Didn't we have like 6 Neos on our climb?
Yes.
Check that out. So now
Part of that was
yeah,
convenience
okay, so now you can
because
create a version.
the gearboxes we wanted to use that were commercial off the shelf only went up to such a high reduction. So we needed a bunch of Neos to be able to use those gearboxes and
To
get
lower
the
the
correct
reduction.
torque. Yeah.
Dang.
Does that make sense? No?
I'm actually kind of impressed with this all does.
Oh.
So basically, okay, so let's do a slight example. So let's say you have a motor that gives 1 foot-pound of torque.
Oh,
Okay.
I would also.
And to
one
climb,
thing is
you
to
need
get it
12
to-
foot-pounds of torque. Or let's say you
See
need
how it's
20
not
foot-pounds of
updated
torque.
over here?
Okay.
In order to update
But
it.
a 20-time reduction,
It's
that's
just
a lot
kind
of gears.
Because we're dragging stuff
So
around,
you're
you
like,
select
dang it,
everything.
there's no gearbox
And
I can
then
buy that has a 21
go-
reduction that carries that much power. So, but if I add another motor, how much torque
Yeah,
do I
that's
have
right.
with 2
And then
motors?
hit root.
And now I only need a 10
10 to
time
1.
reduction. And that might be easier to buy. So that was part of the reasoning for getting 6 Neos, which
So now
is
you won't be
crazy.
able to move
Um,
anything.
Also,
But if you
we
go
made
right-
some
so if
false
you want to
assumptions
move
in the
anything,
beginning.
you
So
have
we
to
assumed
do
we were going to use number 35
But
chain,
if you
which
go
meant
over
we had to
here,
use a bigger
everything's
sprocket,
in the right
which
place.
meant the force on the chain was lower, right? Because if the sprocket's bigger, of course, the force farther out is bigger. Is
This-
smaller, I mean.
this
Yeah.
looks hard.
So,
Because in order to use
so we
these-
overspec'd it quite a bit. But
Kind of
those were
board
the
to be
2
raised
main
up in
reasons.
here, but it's not. Maybe we'll end up putting
So
it on
climbers,
something
just honestly, just throw all the motors at it.
As
If
long
you have
as
extra
have
motors, just throw motors at it. And generally, you want just powerful
Yeah,
motors.
that's the thing,
So,
'cause I think-
again, it's only used very shortly during a match, so you don't have to be as worried about
I think
damage,
we should
really.
we probably should
And
just try it.
like I said, the open motors don't like to be stalled, but when you're climbing, you're not stalling the motor. You're moving up the whole time, basically. So that's okay. Yep. So Neo 775 Pro sim, maybe a mini sim if you're doing like power takeoff or something. Great.
Oh, right.
And for shooters, I don't really
Okay, I
understand.
deleted the-
You just want 3,000 to 6,000 RPMs ish. There's, oh yeah, whatever. If we design a shooter, we'll talk
Yeah,
about
the
that.
nice part about having all this
Great.
is
Now we're done.
so much more space over here. And the nice part
Any
is that when you're working
questions?
on this, you actually remove the battery. But you can't move it any closer
Yes,
because
that's
of
all
this
parts for.
corner, because of how that's connected.
Yeah.
Do you feel like you guys could design an intake or a elevator or a climber?
Definitely not an elevator.
Yeah, why not? I mean, at least the reduction for an elevator.
Well, kind of done.
I don't know.
How
I'm
would
not
you
sure
do
what
it?
to
Can you
do.
walk me through the process?
The elevator reduction.
Yeah.
I mean, I guess the alternative, if you want to
So what's the
time
goal for an
arranging
elevator
it and
reduction?
playing with it, the alternative is probably to put
Well,
the PvP here
With your elevator, you want to
and to fit all the rest of
have
the
it
stuff
go fast,
here.
but then also not stall.
So just
So,
switch places.
Yeah.
Okay.
How about if that's homework?
Or at least
So
you don't
if
want to
wanna
stall it
try-
at a high
if you wanna
voltage.
try it without impacting what's saved.
Mhm.
So do the thing where you create a version.
So if we go back to elevators,
Yeah, hit the create version there, and you can just.
what's the goal?
Like, V1 is fine.
Get to the position as fast as
And you,
possible.
Or in
Please
about
slightly
about a
slow.
second.
Just what was there already.
So you don't need to be especially fast.
No, it's not. I mean, a lot of the things with arms and
Oh,
elevators
is it
is
because we moved something?
you can move them up while you're going to the where you need to put them. right? So like this
Right,
here,
that's the same.
you can pick up a ball and like use the arm to move it to the correct position while the robot's moving.
I don't know what changed.
So it's not like a bottleneck,
Whatever,
the
anyways.
elevator speed or the
Oh.
arm speed usually, except for 1323.
So yeah, just go.
Okay.
Yeah, just save it like that as V1.
Okay.
Okay, so now if you want to try.
Do you know how to design an intake? What do you do to design an intake?
Well,
There's a way to
you have
create.
a motor and then a gear that is the reduction, and that's generally connected to the arm. So,
Ready for the intake? What's the goal for an intake?
you want to also get it to. Oh, oops.
Okay, so the nice
That's
part
not
about
arm.
about
One
having
to two
saving
times the max
conversion
drive speed.
is that if you
So,
change anything from now on, you can always go back to V1.
you
And there's a way.
want to have the reduction.
Oh, because you're only looking at the part itself.
Oh.
So change to the keyboard assembly.
Well, you don't need a lot of
Oh.
There you go.
torque because you want speed. Or
Yeah, it's unclear how much torque you'll need.
so
There's a way to. There's a concept
So-
of ranges.
you don't need to have the reduction, or is it?
So you can have
just
like the
whatever.
like two different.
No,
pieces.
I mean you want as much
I
torque
don't
as you can
remember
get,
that.
right? Because that makes it.
Easier to control.
You just experiment a bunch with the reduction so that you can have max speed and torque.
So it's like you go
What I would
here,
do is I would
and then you
gear the motor down so that it was like 1.5 times drive base speed, right? So I have as much torque as I can get away with,
There's a way to
given
do
the
it.
speed requirements. And then I would try that out and see if it has enough torque. And if it didn't have enough torque, I would add another motor.
Okay.
Yeah. Yeah.
branching design.
This is so much different than when I was in high school, where like
Oh, you're right.
you only had so
And
many
you
of each
branched
motor,
away
and like you didn't have that much power.
Okay, so like let's
Yeah.
say that you
Super
played,
weird.
that you worked on a bunch.
Say that
So you
again?
could
Are the
either
bumpers gone?
or you worked
Yeah,
on
there's
it-
no
Complete-
bumpers.
Completely gone.
I had no my
Like,
freshman year. There was not even an
you can
option to
go
have
back
bumpers.
to- you can write.
Okay, great. I guess I have homework.
Cool.
That you
Right,
don't have to
you
do
can
now.
restore
But
to
I'll
the
give it
beginning.
to you.